share my screen with you guys. I've got one word problem I'd like for you to take a stab at. Here, example 8, talking about Andrew and Stacy riding some bikes. Okay, and hopefully this will be a good little warm up for us. And you guys can remember that distance equals rate times time is sort of the prior knowledge that you're expected to roll into this example with. So go ahead and set this one up in your notes. If you want, you can use a chart. If you don't use a chart, then at least maybe make a little sketch or a drawing or something to that effect. And I'll give you about 2 or 3 minutes to work on this one. So I hope at this point you guys recognize that this is motion in opposite directions, right? And that the way that we write up our equation is going to be not where the distances are equal, but where we have to end up summing up their distances. So there's some unknown time at which they meet. This is just a picture, Portsmouth. And so Stacy's going that way. And Andrew's going this way. Okay. So I'm going to go ahead and call on a few of you guys, and y'all just kind of supply me with what I'm looking for here. We'll start with Alex. Alex, what are we being asked here? Mr. Wendt? All right, so Alex is not answering me. How about Andrew? Jago?
We're being asked what time they meet.
All right, so the relationship between time then is where we've got that piece of prior knowledge, right? We've got this formula that we know distance equals rate times time. Okay, so Charlie, can you solve that formula? We practiced back in section 2.3, manipulating formulas. So Mr. Griffith, go ahead and manipulate that formula. Get it to where t is by itself. What is t therefore equal?
T equals E divided by R.
Very good. T divided by R. We got distance divided by rate. Okay. So if we're asked for what time they met, it's probably going to be a good idea to at least have a understanding of how I would find, for instance, how long Andrew has been writing or how long Stacy has been writing. Okay. Now, which one of them will have been writing the smaller amount of time? Alex, I see your note where you said you're trying to fix your mic, so no worries, buddy. Which one of them has been trying to ride for the shorter amount of time? Because I like to let my unknown stand for the shorter or smaller quantity. Colin, how do I figure out who has been riding for less time? Kozlowski?
Do you divide their rate of how fast they're cycling by the time they left?
I think it'd be a little simpler. Let's look at these two highlighted portions right here. And so use a little common sense here. Who do you think has been riding for less time? Andrew left at 9:30.
Stacy.
Very good. Stacy left at 10, right? So when we look at their time, why don't I say let X equal Stacy's time? Okay. And then Andrew's time is going to be X plus what, Daniel Thompson? Daniel, you hear me? Apparently not. Let's throw it over to Jack McBee. How could I express Andrew's time? And be careful here.
Andrew's time should be X plus 30.
Ooh, let me backtrack up here, and I'm gonna make sure we see this note from last week. Make sure the time and the speed match in terms of their units. So although it's 30 minutes, we've got our rates are expressed in miles per hour. So X plus what would be a better idea?
0.5 miles.
All right, so let's just say 1/2, or 0.5 would be fine, but let's just say 1/2. Okay, so that's going to equal Andrew's time. Okay, now we also know Andrew's rate, which is 12, and we know Stacy's rate is 16. Okay, so what we can do is we can wind up multiplying, again, rate times time to equal that distance. So here we've got, I'll do it in blue actually to color code it. We got 12 times quantity X plus 1/2. That's going to be Andrew's distance. We've got 16 times X. That's going to be Stacy's distance. Should I set those two equal to each other, Joe? What do you think, Mr. Edwards? Should we set those two equal to each other?
I'm not sure.
All right, let's read the last little bit of this problem here. We have not made use of that information yet. It says the distance from E to P, the distance from Exeter to Portsmouth, is 20 miles. So if I've got, in blue, if I've got this far that Andrew has ridden and this far that Stacy has ridden, what can I do to write my equation, Joe? What do you think?
Subtract them.
We're not going to subtract them. All right, look at my picture here. This is the amount of distance that Andrew has ridden. And this is the amount of distance that Stacy has ridden. And from here to here is 20. So I don't want to subtract, I want to
Add them.
Yeah, we're going to add them up. We're going to add them up and we're going to set them equal to that 20. okay? Because if Andrew covers a certain amount, and like for example, like let's say Andrew covers 5 miles, then Stacy will have covered 15 miles. You know, that's the idea, that we add them up together. Okay. All right. So we can use our distributive property. Go ahead and do that. 12x plus 6 plus 16x equals 20. Let's combine our like terms. At this point, it should be real quick and easy, right? 28x. This is step number 4 of our word problem solving method. Let's subtract 6. So we got 14 is 28x, and let's divide by 28. X equals 14 over 28, and that's going to simplify down to 2/4 or 1/2. Okay, so if x equals 1/2, Jake, make sense of that answer for us. It says find the time when they met. So if x equals 1/2, how do I answer the question?
Well, if x equals Stacy's time, or I'm not sure.
Well, no, you're right. You're right. Look, if x equals Stacy's time, and that means that she's been riding for half an hour. When did she start riding?
Half an hour ago, or 15 minutes ago.
Look at the green highlighted up at the top. It tells you.
She started at 10 a.m.
So she's been riding for half an hour, and then they meet.
10:30.
Yeah, very good. 10:30. So this is, guys, this is a great example of when the solution to our equation does not necessarily answer the question for us. We've got to make sense of the solution to our equation. All right, so like I highlighted, this question was all about time. I highlighted the time at which Andrew left. I highlighted the time at which Stacy left, and then I highlighted the question, well, when do they meet? And we wrote up our equation, rate times time equals distance, rate times time equals distance, add the two together. And then we said, okay, we solved that out. We got x equals 1/2. And then we said, oh, well, if she's been riding for half an hour, then they must have met at 10:30. And that makes sense because look at what Andrew's time was over here. Andrew's time was x plus 1/2. Well, that means how long did Andrew ride his bike?
No.
He rode for a full hour, right? So if x equals 1/2, then that answers our question for us in a sort of a roundabout way. Okay. Any questions that you guys would like to ask about that rate, time, and distance question?
So if Stacy was X and he was X plus 30 minutes, then he would have just how would he have rode an hour if it's plus 30 minutes?
So because 30 minutes in terms of an hour is half an hour. Okay, so that's the key thing there. I think I was telling Jack this a minute ago. So Lewis, look up at the top here. Here's our note again, where it says, okay, we want to make sure that our units of time match. So in other words, Stacy's time, she rode for half an hour. That's also known as 30 minutes, right?
Mm-hmm.
Okay, so if she rode for half an hour, and Andrew's time over here we had expressed as x plus 1/2 an hour. Okay, so a half an hour plus a half an hour equals a whole hour. And that makes sense. If Andrew left at 9:30, then a whole hour past that would have been our answer again at 10:30. Okay, so
Okay.
Lewis, the notion is that if Stacy rode for 30 minutes, then Andrew must have ridden for 60 minutes because he had a half hour start. He had that 30-minute start.
Okay, so you add that.
Yep. Because that question in blue, it could have very well been written differently. It could have been, hey, how long did Andrew ride? Or, hey, how far did Andrew cover? What was Andrew's distance? And what we ought to be able to do, fellas, we ought to be able to answer any question that they possibly ask us about that, right? For example, what if we wanted to know how far Andrew's distance was? If we wanted to know how far he rode, well, we would just multiply the rate times the time to get that distance. And he rode for an hour at 12 miles an hour, so he covered 12 miles. And Stacy wound up covering 8 miles because she wasn't riding as far. She rode for half an hour at 16. So half of 16 is 8, and that makes sense. So Andrew covered, see my picture's off kilter a little bit. Andrew covered more distance than Stacy did. All right. Y'all got any other questions? Thank you, Lewis, for that question. Anybody else? All right. So we're going to shift gears then. And for the last little bit of class here, we're going to talk about inequalities. Okay. We're going to talk about inequalities. I've got a little warm up for you here on the screen. This is not too bad. So I want you to do a couple of these problems real quick. It says translate from algebra to English. In other words, write down in words what this expression says, and then go backwards. So we want to translate from algebra, or from rather from English to algebra, what this expression right there says. Okay. All right, Luke, what is this first one? Translate it from algebra into English. So all you got to do is just read this out loud for us. What does this expression right here mean in English?
15 is greater than x.
Perfect. That's easy enough. That's our greater than symbol. All right, very good. And then John, what is this expression down here on number 2 written in math? What do I do?
Put 15 and then a less than sign and then x.
Yeah, easy peasy lemon squeezy, not hard at all, right? And the importance, fellas, is understanding with inequalities, the importance of understanding, I'll use the elementary school way of looking at which way is the alligator facing. He wants to chomp more, so it's, the larger value is over there. So in doing these kinds of questions today, what we're going to be looking at is we're going to be looking at how each of those inequality symbols stacks up, okay? Looking at this chart right here, for example, okay, I pulled this from our textbook, but I really don't like how they do it. They use a parentheses in our textbook for the open interval. So in other words, for when you're not including that point, I'll use an open mark. I want you to get used to doing an open mark, and they use a bracket in our textbook when they're wanting to include, so like it's x is greater than or equal to something, right? They want to include it. I'll use a closed mark, okay? So bear in mind that difference right there. If you are a textbook reader, I don't know if you guys go through and read the textbook any, but the notion of graphing out an inequality on a number line shouldn't be something that's completely new to you guys. It should be something with which you're fairly familiar, okay? So like when we look at a number line, we ought to be able to tell very quickly, is he including or excluding that point, and which direction is he shading? Okay, so we'll have one of those two things to concern ourselves with. Does he include the endpoint, and where is he shading? That's how we would graph out linear inequalities on a number line. Okay, with a nod of a head or a thumbs up or a thumbs down. Have you guys done much of this before? Okay, sweet. Usually this is not something new that you guys have to struggle with. This is a pretty easy lesson to deal with. So let's practice with some easy examples. First of all, example 1, part A. Okay, so I'm going to use a number line here. And you guys will like how I do this because I don't require you to put like 0, -1, -2, -3, -4. I don't require you to put all those. Whatever value you're at, just put that in the middle of your number line. You know what I mean? And then are we going to use, Joey, are we going to use an open or a closed mark for this one, for part A?
Closed.
Yeah, because it's including -3. All right, so we're going to put a closed mark right there. And then Mossy, should I shade to the right or to the left? Valentino, I couldn't hear you. Type your answer in if you want to. And so I'll give you guys a little mnemonic device. You got to listen to me as I say this though. This phrase right here, I'll highlight it in yellow. This phrase right here is not x is greater than or equal to -3. Oh, no, that's not how we say that. We say x is greater than or equal to -3. What am I emphasizing there? I'm emphasizing the r sound so that I can remember to shade to the right. So if it's greater than or equal to, we're going to shade to the right, which I'm assuming Mossy has typed into the text at this point. All right, so we're going to shade. And what does that mean? That means that any number at -3 or greater than -3 to the right is going to be giving me a true statement. So like I could plug in the number 0, for example, and I get a true statement there. 0 is greater than or equal to -3. If I were to try and plug in a value over here, for example, like the number -5, that would not be a true statement because -5 is not greater than or equal to -3. You see, that's what we're doing, fellas. When we graph linear inequalities, we're graphing the set of numbers that makes a true statement in the inequality. And that might bear writing that down. I'll try and type it in pretty quickly here. But the graph of a linear inequality is the set of numbers that makes a true statement in the expression. So in other words, when we talk about solving equations, for example, our definition for solving equations is the exact same. You're solving an equation, you're finding all the numbers that make a true statement when plugged in to the equation. Well, here we're finding all of the numbers that make a true statement when plugged in to that inequality. All right. The second one here is going to be x is less than 2.5. So we're going to use an open mark at 2.5, and we're going to not x is less than 2.5, it's x is less than, so we shade to the left. All right, that's an easy mnemonic device. And then another mnemonic device that you might have heard before, your teacher probably has told you this one. If the variable is on the left, like for example here, it's almost as though I could draw an arrow and that points to where we should shade. Did you guys know that one already? That if you've got an inequality sign, it's almost like an arrow pointing you in the right direction. Now, where that breaks down is if I've got my variable over here, you know, whoops, I put X on both sides. If I've got something like this, then I don't want to shade to the left. That's not what we're talking about. So that mnemonic device sort of breaks down a little bit if I've got my variable on the wrong side. Okay. Last but not least, we got x is less than or equal to, so we put -3/5, closed mark, and we're going to shade to the left. All right, any questions on example 1? Easy stuff, right? Now, I want to introduce something new. And actually, I'm going to give myself a little bit more space for this one. One day in the not so distant future, you guys are going to take calculus. You might even take calculus from me. Who knows? But when you take calculus, you will be required to start using what's known as interval notation. Okay? Now, interval notation is how we express a set of numbers in a concise and consistent fashion. Okay? In algebra, we oftentimes use inequalities. Just like you see here, we got 3 sets of compound inequalities written up here. Okay? And that's all good and well for algebra. But in calculus, we want a shorter way of expressing this. So let's do both things here. They ask us to graph each one on a number line, and they ask us to use interval notation. So let's take this first one and look at it together. Okay? So on my number line, I'm going to put -3, and I'm going to put 4. Okay? And I want to note which kind of marks I should use. Should they be open or should they be closed? What do you guys think?
Open.
Open on both ends, right? We are excluding -3. We are excluding +4. Now use a preposition and describe for me the set of numbers here that would make a true statement. Okay, Nate, what preposition would you use to describe my set of x values in relation to -3 and 4? Nate, you know what I mean by preposition? Earth to Nate. All right, Paul, we're kicking you up next.
Greater than.
Wait, what's that, Nate?
Greater than.
No, son, preposition. Parts of speech, right? We know our parts of speech, don't we? I'll give you a hint. It starts with B. Where are my X values, in other words, in relation to 3 and negative, or negative 3 and 4?
Between.
There we go, between. I think maybe Paul snapped that one, so sorry, Nate. Yeah, here are my X values. They are between negative 3 and positive 4, okay? Now, the way that we express that using interval notation is that we're going to use a parentheses when it is an open mark, and we're just going to write up the numbers sort of like we would see an ordered pair. That seems very strange, I know, but that's what's known as interval notation, to where you don't have to do any kind of graphing. All right. Part B, let's look at part B right here. -6, -1. And here we're going to use a closed mark on the left and an open mark on the right. Okay. Again, because the closed mark, it's inclusive on the left endpoint, and here it's exclusive on the right, strictly less than. And again, we're going to use this notion of being between. So there's my graph. Okay. But for interval notation, when it's inclusive, I'm going to use a bracket. Do you guys note that subtle little difference there? And this is why, by the way, our textbook does like they do when you saw back there a moment ago, where they were using brackets and parentheses. They were trying to introduce this notion of interval notation as well. All right, so when it's a closed end point to the interval, we're going to use a bracket. And then last but not least, this one over here from 0 to 2.5. Right, we're going to use a closed mark. Okay, on both sides. Again, X is between them. So that means that any number between 0 and 2.5, including 0 and including 2.5 would work. And so for this interval notation, we're going to use brackets on both sides. Okay, so in other words, parentheses are used for interval notation when it's excluding the endpoint. And brackets are used when you are including the endpoint. Okay, that's what's known as interval notation. So for you guys, you just learned a little bit of calculus, at least notation-wise. You know what I'm saying? So like, I'll show you what I mean. We're studying logarithms right now for calculus. So here's what they're going through. Y equals the natural log of x. And they know that the graph of such a function looks like that. And I would ask the boys, I would say, hey, can you tell me the domain of that function? And you don't have to know any of this, by the way. But when they get to listing the domain of that function, what they do is they write up, oh, Coach Morgan, it starts at 0, but it doesn't include 0. And then it goes on and on and on to positive infinity, and 1 could never equal infinity, so we would use a bracket there, for example. All right. Or maybe they would have like the function y equals x squared, which is a quadratic graph. Right? And its graph would be a parabola. And I'd say, hey, could you please for me, tell me the range of this function? And so that, oh, okay, Coach Morgan, it starts down there at 0. That's the lowest that it goes, and it actually equals 0, and then it goes up on to positive infinity, and you can't equal pi. Well, this is that interval notation that you guys just learned about. So it's a way of noting things in a calculus context that you guys will rely upon, you know, in 2, 3, 4 years, whenever you guys start taking calculus. Okay. All right. Questions on example 2 at all? All right. Let's wrap things up then with this notion of solving. Now, solving inequalities works the exact same way, and we won't get through but just one of these today. Works the exact same way of solving an equation. We use inverse operations, you know, changing sides, changing signs, and so on and so forth. We move things around to get x by itself, let's say. All right. So for this first example, I've got x minus 3/8. less than or equal to 3/4. Okay. What can I do to both sides to get x by itself?
Add 3/8.
Add 3/8 to both sides. That's all she wrote. X less than or equal to 3/4 plus 3/8. Okay. And so we add those two fractions together. That's going to be 9/8. X is less than or equal to 9/8. Okay. And it says to graph that on a number line. So I'm going to use a closed mark. Here's 9/8. I'm going to use a closed mark. I'm going to shade to the left since it's less than or equal to. And then interval notation. I can't equal negative infinity, but that's my left side. And then my right side is 9/8. Because this one goes on and on and on infinitely to the left. You can never equal infinity, but you can go towards it. So that's why we would use a parentheses on the left side and then a bracket on the right side because we have it less than or equal to 9/8. Okay. So in a nutshell, that's what we are doing, fellas. In this section, we're going to be solving inequalities. And the inequalities are going to get more complicated. We'll talk about a couple of little caveats that we'll encounter when solving linear inequalities. And then we'll start looking at more compounded inequalities probably later on tomorrow. But any final questions that you guys have for me? All right, then. Well, hey, I appreciate your hard work, fellas. I will probably put up a homework assignment through deltamath.com this week for you guys to chew on, and I'll post the announcement for that in our general channel here on Teams. But y'all have a great day. Thanks again, and see you tomorrow. Live Jesus in our hearts.
Forever.
Wherever. All right. Thanks, boys. Y'all take care. Be safe out there in that rain.